Welcome back to Element 14 Presents. I'm Clem and I have a dream of a bus system that goes throughout my workshop. Not like Ethernet, but like just two wires that make all the devices communicate on their own. Like I2C. Hey, that could work. Yeah, there are countless sensors and microcontrollers and whatever that can just talk over I2C. But that is only meant for connections on a PCB, like between two circuits. That's why it's called I2C, like inter-circuit. The name isn't really logical, but it's meant to be between circuits on a PCB. But how far could these connections actually be? There's only one way to find out. Usually I don't really Google around, I just start with my projects, but this time I really wanted to know first if it's even possible to have I2C go for more than a few centimeters. So I Googled around and it turns out it seems the recommended limit is a meter, like 1 meter, and the length that it can traverse is dependent on the capacity of the whole system. So there's the capacity of the trace or the cable, there is stray capacitance, there's the capacity of the circuits on the bus, so each device adds more capacity to the bus and there's a limit to it. And also speed seems to be an issue. So I think I should go for the standard bus speed, which is 100 kilohertz, and see how far we can go. May I introduce you to our test subject, the humble Raspberry Pi Pico. I chose this microcontroller in particular because it is a microcontroller. And I can control it with the Arduino IDE, which has an I2C implementation, the wire library. And this works on this microcontroller, and having two of those allows me to make devices that controllably talk over an I2C bus. I don't have to fiddle around with a specific sensor that talks over I2C, find out its protocol, and then see if it still delivers plausible data over a longer distance. I can deliberately program two microcontrollers to issue commands and show if they have correctly received those commands and execute whatever function was sent. So that means I can deliberately test them. But there's more to this thing than just having a microcontroller. So I told you that capacitance on the bus is the main thing that we have to be concerned about. So how do you get a set capacity over a longer distance? Impedance controlled wire. This is a roll of RG58. This is coaxial cable, precision coaxial cable with 50 ohms impedance. That means we have a controlled impedance or a controlled resistance over the whole range of this. So every meter of this will have 50 ohms. So we know that the impedance will be constant along all the length of this. If you use just some random cable, this can vary. We don't know any capacitances that could be different along the way. This is shielded. So we have a shielded outer wire mesh that will be grounded, and in the center there is a conductor for our signals. So if we use this cable for our tests, we know that under ideal circumstances, which means controlled impedance and a shielded trace, we know how far I2C can go. Yeah, this is a bit heavy. On the web I found a lot of conflicting information about how far people think it can go or how far people made it go. The thing is, the longest claim that I found was 2.5 meters for a 100 kilohertz bus, and this was with a controlled impedance cable for a sensor. This is the only example that I found that is practically used out there, on a daily basis. It's basically a sensor cable. So my concept would require this to go about a lot more. So I think if I can make this go over 10 meters, that's quite a lot, then I know I can pull off my idea, because most of the buses will be about like 5 to 7 meters maybe. If I can get to 10 meters, I think I'm gonna be good. So I have this ideal cable, basically an ideal test trace, but I don't have an ideal connection scenario. I don't want to directly solder to the pins because I may have to change stuff during this project. So I'm using a breadboard, stick my Raspberry Pi Pico onto there. I use an LED for the outputs, a button for inputs, and I connect my cable just with header pins. That's it. So these should also add a bit of like additional resistance, maybe some stray capacitance to model a bit of a more realistic scenario where there are some things that are not ideal. If I would deploy the solution, of course, I would like completely terminate them correctly with BNC connectors, for example. And then with just a little BNC connector, you can just plug into the whole bus system that would then go around my workshop. I have prepared 10 meters of RG58 and another 10 meters of RG58. Why 20? Because I2C needs 2 lines. I will try to make the connection with just one cable. That means one of the conductors will have the clock signal on there and the other one the data signal, and then we'll do the same thing but with both connected. So it's clock and data on the inner conductors and then ground for shielding. This, I think, should yield me like a full 10 meter run. And if that doesn't work, we just cut it down until it works. Let's address the yelling commenter in the room. Clem, why are you so dumb and not use CAN bus? Why I2C over big distance? It's not made for this. CAN bus is made for this. RS485. You just need a CAN bus system throughout your workshop and everything is fine. Well, nice commenter, you're absolutely right. CAN bus would be like a great system, but you would have to have a CAN bus transceiver on every single device on there. And I2C comes for free with microcontrollers, basically. So either I have like I2C sensors, which of there are plenty, and I would have to make I2C to microcontroller to CAN bus to make them usable on the bus, or I would have like microcontrollers plus a CAN bus transceiver, and then so I can also like just go directly I2C. It's just cheaper. I'm frugal. It's just the way I roll. But of course, you're right. CAN bus is better. But that's not our project today. Today we test how far I2C can go. CAN bus maybe next. Our test setup has 2 ends. Of course it has. On one end there's our RP2040. On the other one there's the same. But this one has an RGB LED on it. The other one has the same. Okay, but now the difference is this one has a button. And if you press that button, it sends out I2C commands over I2C. And each of these commands corresponds to a color on the LED. So it sends a 1, a 2, and a 0 in hex, corresponding to the colors red, green, and blue. Red, blue, and green. That's the... yeah. And it will send that over the bus, 10 meters across, and then to the other one. But first we have to make sure that they even work at all. So first we set them up just with a direct short cable connection and see if it even works. On the second end, I have added this little extra LED. This will always light up when there has been a signal correctly asserted. So if one of the received bytes is 1, 2, or 3, this thing will blink. So if it by coincidence gets any other commands, like the data has been corrupted or whatever, the LED might still light up because by coincidence the numbers matched, but this LED will only light up if the data is exactly what we're trying to send. So this is hard-coded. Yeah, speaking of code, there's a bit of code. Let's check it out on my computer. Welcome to the Arduino IDE. I use this to program the RP2040. It's one of many ways that I can use it. It's my favorite way. We're using the wire library to do our I2C implementation. This is a built-in library into Arduino. And this code has mostly been written by a large language model. I had to
change quite a lot of things. So don't rely on LLMs now that they write your code, but I wanted to give it a try, and hey, it did nice annotations, so you know all the stuff that it does in each line. At least that's a given. I had to do a few changes to make it work. But yeah, so we have a few LEDs. If we have a button, these LEDs are actually one RGB LED, but in code it doesn't matter if you have more than one. We have to set our I2C address. This is the code that sends out all the signals. What we do whenever we read a button that is low, that means the button has been pushed, we send 0.1, wait a bit, send 0.2, send 0.3, also light up the LED that we have on our Pico here, so we know which thing has been sent. That lights up after sending, so we might see the LED on the other end light up before we can see this one, because there's a bit of a time difference, but signals on wires can be very fast, so they might overtake. This is done with a custom function, send and illuminate. It called it illuminate because I told it to illuminate LEDs, not turn them on. So if I would have called it turn on, it would basically maybe call it send and turn on, which would be funny. Anyway, so we have an LED pin, the I2C address, which is fixed, and the value that we need to write here. And that is basically all it does, plus the turning on and off of the LEDs. The second piece of code is pretty much the same address, of course, because this is our target that we wanted to reach. The difference is if this registers an I2C event, which you do in by registering, really hard word, a callback, it will execute the callback on receive, which is a function right here. And this will basically read in the values from the I2C bus and then turn all the LEDs off, then read if this is a valid message, which means it's one of these three cases, turn the corresponding LED on, and also if the message is one of these, it will then also illuminate the extra red LED on there, so we know it has actually received a value that is in the list, not a corresponding value or like something that adds up to it. Like we basically want to rule out any data corruption that yield to still turning on LED. So maybe like some glitch or whatever. So if they both do what we want, then we know it is an actual I2C command that has been received and not a coincidence that made the LEDs light up in the same sequence.
Okay, so we now know the transmission works. Does it also work over 10 meters of cable? That's our next experiment. And with that working, we can then also have the power connections going over these 10 meters and see if we can just connect a remote device onto this bus and still have it powered and communicating well. Lesson of the day: communication works over the 10 meters, but not power. The power drop for a 3.3 volt system, or even if I transmit the 5 volts bus voltage from my USB devices onto the bus, that has too much voltage drop over 10 meters. So directly powering the whole system doesn't work at these low voltages. That's why PoE basically has like higher voltages and that then get transferred down and stuff. So to have like account for the loss over the distance, because like resistance over distance times voltage and current and, you know, Ohm's law. So we have to power our device externally if we want to have it on a 10 meter bus. So each of these devices have to have their own power source. That means if we make basically like sensors that have like a little coin cell on there and we only wake them up whenever we need data from them, that could be a quite viable solution. So we now have a setup where there's 10 meters of coiled wire and even more 10 meters of coiled wire set up onto microcontrollers next to each other. So they send the signal that goes through all the 10 meters and then back to the other microcontroller, and we see that the data still arrives. But there's this theory that the length of wire doesn't really matter when the recipients are close together, because power and current is not actually like physically flowing in the wire. They are not electrons moving, they are just like states or potentials passed. So there could be a difference in if they are close to, if like the endpoints are closer together or further apart. That could also be capacitive coupling. But it's all very like RF esoteric in that field, so I'm not the expert on that, but I know how I can test that. And that is by stopping to coil my wires and extend these wires in a straight line, just out of this window. Yeah, my workshop has a connection to the outside, believe it or not, so sometimes I can even leave it. We might have to wait until the sun comes up again. But then I'm moving half of my project outside and see how far I can stretch the cable, and that still works. Drück noch ein paar Mal. Ja, drück noch ein paar Mal. So the most important question is, did this control impedance cable allow me to transfer I2C for 10 meters outside my workshop? The answer is yes, it did work. Did I try with 20 meters? The answer is also yes. Did it work? No. There is some point where voltage drop also in signals comes into play, and I think 20 meters is just too much. But 10 meters was perfectly reliable at 100 kilohertz, so I didn't even have to slow down the bus. 1 megahertz also worked. So I would say 10 meters, that is a comfortable length with controlled impedance cable to run a bus. If you're doing this on like some random cable, maybe a power line or whatever, you might get different results. So, but for my project, I know now, I now know how to approach this. If I get that crazy. I will probably get that crazy. We have two ways to make this better. In another project of mine, we explored the possibilities of running I2C on an ATtiny with a custom I2C implementation. And I will probably use that because, hey, I'm a frugal guy. I want to have like a cheap bus system on there. That's why I2C was used. And I want to have cheap microcontrollers on there. That's why ATtiny comes into play. So these projects basically merge together in an unholy alliance. And I also wondered, could I do a one-wire system where there's only one wire on the bus, so I wouldn't even have to run a second of these? Turns out I couldn't find an implementation that allows me to have communications between two microcontrollers on one wire, just between a sensor and one wire, because the one wire thing is like a proprietary I2C variant. So if you know if we could make like I2C go just on one of these coaxial cables, that would be very awesome. Maybe we don't even need the shielding if the environment is not that noisy. Yeah, but there's a way forward. Ladies and gentlemen, the results are in. How far can I2C go? Well, this far basically. So either 10 or 20 meters if you have a controlled impedance cable for that, or even further if you use ICs that are I2C repeater chips. So you can always extend them with further 10 meters maybe. And that might be a really awesome project for my new workshop. Anyway, I gotta go. There's another project waiting for me.